There's something else that we can do here with these fields. We're going to define right off the bat. And really, if you know Cartesian products already, then this is nothing new. But the book defines lists and tuples. And these are both things that are similar to the Python list and the Python tuple as well. So the book starts off by just remarking that many of you have heard of R2, which is the set of pairs, x, y, so that x and y are real. And of course, you could define R3, which is the set of x, y, z, so that x, y, and z are real. And this is also described as, or by definition, it's equal to R crossed with R, and this is R crossed with R crossed with R. Because that's what it means to take the Cartesian product. You're taking ordered, well, if there's two elements, you're taking ordered pairs. Here we're taking ordered triples, where each of the things comes from the set that's given. So the book calls this process, the book calls the set of these things the set of lists in R of length n. And it has a note that some mathematicians prefer to use the word tuple to list. And Python does both, but I might interchangeably say tuple or list here. In Python, bracket notation, like closed bracket notation, would be used for lists. So if you had something like that, that would be a list, and this would be the tuple in Python. And there are definitely some very big differences as to what you can do with lists and tuples in Python. But there are also some things where it might seem the same as well, and that is something not for this section of this book for us to talk about. But the book uses this notation, and they call it, quite often they call it a list, but they mention it's also known as a tuple. And what can we do here? Well, we can do this, whatever our field is, we could take a tuple of length n. So for example, if we want our field to be F2, and I want to take tuples of length 4, what am I going to get? Well, I'm going to get, I'll have 0, 0, 0, 0, 0, 0, 0, 1. And how many of these do I get? 0, 0, 1, 0. Well, we have two choices for each slot, and we have 4 slots, so that's 2 to the 4, which is 16. So I'd have things like this. And we can use the same sort of shorthand that we do here for R2 and R3. We could say, okay, we have F2. I want to put that in parentheses so we really know what we're talking about, because it might be a little easier to read. We say, hey, this is the field F2, and I'm taking that to the second power, or I'm taking that the Cartesian product of that with itself. That's a better way to think about it. We could write it like this, and this would be tuples of length 2 in F2. So we'd only have this, 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 and this. And that would be what we would have there. Now, what we don't want to do is we don't want to try to come up with a multiplication of these tuples or these lists, because even with the complex numbers, in order to get the properties we wanted, hopefully we saw, we couldn't just straight up come up with the most simple definition that we might have thought of for multiplying. We definitely don't want to multiply pointwise, otherwise we miss out on those important axioms. But our solution is not to multiply these lists at all with each other. What we're going to do is we're going to have two operations that are introduced in this section, and one is addition and the other is scalar multiplication. So addition is going to be pointwise. So for example, if we're in the rationals, let's say we're in Q3, and I have 1/2, 1/3, and 1/4, and I want to add 1, 2, 3. And what I do here is I just add pointwise. So I add whatever in the first slot. So I'd get 1/2 plus 1, 1/3 plus 2, 1/4 plus 3. So this would give me, of course, this is the hardest part of the lecture, 3/2, and then 7/3, and then 13/4. So we add pointwise in the set of lists or tuples. And if we do this, there is sort of an additive inverse and an additive identity. And I can't say we have an inverse until we have an identity. So there's an identity and there's an inverse for each element. And what would that be? Well, if I'm taking tuples or lists over a field, right, I have a 0 in the field. So whatever I have, if I have, and there's one other thing I want to do for the first time here. So since I'm doing this for the first time, if I just use capital F, that means I'm working in a field, but I'm not telling you what that field is. So I can use just a big capital F and I can say, hey, I'm working in a field, it's F. I'm not telling you what that field is. So here I have F to the n. So this is the Cartesian product of my field with itself n times. We don't know what the field is. We don't know how many copies there are. Some number, n. Hopefully it's a positive integer, so this makes sense. If it wasn't a positive integer, then this wouldn't even be defined. But let's say I'm adding elements in Fn. So what could I do here? Well, I have some x1, x2, x2, x3, through xn. And I want you guys to notice something. If I were to add just the same tuple, that's just the additive identity, over and over again. By the way, when I use this dot, 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 that just means and so on and so forth, of course. So this is going all the way up to the nth element of my list or tuple. If I add this, what happens? Well, I'm adding it pointwise, so I get x1 plus 0 in this first slot, x2 plus 0 in the next slot, and so on. Well, that gives me x1 plus 0, x2 plus 0, and so on, all the way up to xn plus 0, which is just the same thing as x1, x2, all the way up to x sub n. So this acts as an additive identity. Now, I haven't actually proved that because I have to show it's the same on the left and the right, but you could see that it's going to be the same on the left as well because I just have the zeros on the left. So when I have this collection of lists, or the Cartesian product of a field with itself, what I can do is if I define addition to be pointwise, I have an additive identity. I also have an additive inverse because I know that x1, x2, all these numbers through xn, they each have an additive inverse. So if I say call the additive inverse of x1 minus x1 and minus x2 and so on and so forth, if I take x1, x2 through xn and I add minus x1 minus x2 through minus xn, well, I know in the first slot I have x1 plus its additive inverse, so I get 0 and 0, and all these are going to be zeros. So this is not going to create a new field. Taking a field and taking n copies of it, this does not make a new field. But what it does do is it makes a place where we are still allowed to add, and we have an additive identity, and we have additive inverses. And there's something else we could do. We're going to want to be able to multiply a list by an element of the field. So for example, if I have a lambda in F, what I could do is I could define lambda times this list, and I could say, okay, what is it going to be? Well, I'm just going to apply it everywhere. So I apply it to each of the elements. So that's an operation. And because we have a 1 in our field, we're also going to have, it's not an element of the list, but we have something that fixes our elements in our list. And that's really all we can say. We don't have an element that happens to be a list that fixes things because we haven't defined multiplication between two lists. But we do have this action of scalar multiplication, where we multiply a list by a single element of the field.